Hello, I'm Price Dehars, and in today's lab, I will show you how to get the weight of a mass using the weight of two strings in equilibrium. First, we'll start off with the materials. You're going to need 2 spring scales measured in newtons, 2 ring stands or anything to hold your spring scales, some string, and an object, of unknown mass. Now for the setup of this lab, we hung 2 ring stands and spring scales from those ring stands. We tied strings to the spring scales together, made a knot, and hung the mass from that string. It doesn't matter if you make a knot or tie your strings directly to the mass itself. In our particular experiment, the left spring scale read 2 newtons and the right spring scale read 4 newtons. Setting up a free body diagram is always a must for this type of experiment. Now, when an object is in equilibrium at an angle, the angles must be found. I'll do that in a little bit, but it's good to visualize what you're trying to find. So what we're trying to find is this blue value here. Some of this 2 newtons and some of this 4 newtons is going to be displaced along this green dotted line. So you can't just add 4 and 2 and then get 6 for the resultant vector of gravity. To figure this out mathematically, I will now do sum statements. The way that the angle comes off the top makes the x value cosine, which is this green dotted line right here. Because the object is in equilibrium, we know that both the x and y's cancel out. But in this case, we're looking for the mass, which would have to deal with the force of gravity. So the x's, which would be the tensions, the cosine of the tensions, would equal 0. Which means that the cosine of less tension is equal to the cosine of the right tension. For the y sum statement, however, is where we're going to be doing most of the math here. And as I said before, the way that the angles come off the ceiling, these y values are going to be the sine of this angle. And as I said before, in these x values, these y values are also going to equal 0. But the reason why tension left and tension right are added up and not subtracted is because right here is the x-axis. These 2 tensions are on the positive side of the x-axis, while gravity is on the negative side. What we did next was set a piece of paper behind the strings and draw a point where it comes into the paper, the point where your knot is, and the point where the string goes off the paper. Then with a ruler, I'm not using one, but we used one during the experiment, you would connect the lines and make this general shape. Now, it's not perfect, but that's sort of what we did. Our measurements came out to 13.4 centimeters and 9.1 centimeters. Now, you could use a protractor and you wouldn't have to measure these lengths, but using trigonometry to figure out the lengths other than a protractor is much more accurate. Group, we had 9.1 centimeters for tension left and 13.4 centimeters for tension right. In our lab, we took 8.5 centimeters and did inverse sine to figure out the angles of theta and alpha. These will become important when we substitute these numbers into our sum statements. Now, if you think back to the original sum statements I made, you can now plug in the numbers that you have obtained. Theoretically, this should equal 0, but it's not going to because this isn't a perfect lab. And whatever number you do have will represent your margin of error. But we're not going to calculate for this. We're going to calculate when we actually measure this mass. The purpose of this lab, however, is to figure out how much the mass weighs. And to do that, we have to figure out our y values. Or if you want to think about it, how much gravity is pulling on the mass. The whole point of this lab is to find out the force of gravity, which is this equation right here. And if you finally substitute all your values in for theta and tensions, you get a number in newtons. Because we measure the tensions in newtons and the angles, well, they don't change, our answer will be in newtons. And with all of these numbers taken into account, this ends up to be 5.00 newtons. After calculating the mass weighed 5 newtons, we had to physically weigh the mass that we had with either a triple beam balance or an electric scale. In this case, we had to use a triple beam balance because no electric scales were available to us that went over 200 grams. The mass ended up to be 497 grams, which is equal to 4.87 newtons. Our percent error came out to a respectable 2.67%. Now, the reason why we got any error at all is because of several reasons. One, manual spring scales, they don't work as well as electronic ones. Reason number two, if you have your lines, instead of using trig, you could use a protractor and measure this angle. That's not the most accurate thing. And the third one is, on the manual spring scales, the numbers are a bit difficult to read, especially in newtons, because you can only get up to just about a quarter of a newton. And also with spring scales, if they're not calibrated correctly, your values will be off. In conclusion, this lab shows how to mathematically calculate for mass by taking the resultant tensions, in this case 2 newtons and 4 newtons, breaking them down into components by using trigonometry, sine and cosine, and using those components to find an unknown mass.